Welcome to Brain Vision.
So in this question, we want to compare the amount of energy released per gram of fuel. In part A, we look at gasoline, and when gas is burned, it released 1.3 times 10 to the 8th joule of energy per gallon. And then a gallon is 3.788 liter, and then the density is 737 kilogram per meter cube. And we want to express this quantity of energy in terms of joule per gram. So it's really just unit conversion. So for part A, let's do for each 1 gallon, the mass, for each 1 gallon, the mass equals rho times V equals 333 kilogram per meter cube times a gallon is 3.788 times 10 to the negative 3 meter cube. So this is 2.79 kilogram. And then we know that this amount of fuel will produce 1.3 times 10 to the 8th joule. So the amount of energy per mass is 1.3. Actually, we want the amount of energy per gram, so we also need to convert kilogram to gram, times 10 to the 9 times 10 to the 3rd grams. So this gives us 4.7 times 10 to the 4th joule per gram. This is the amount of energy per mass for gas. Then for part B, we says, well, during fission, a nucleus has about 200 MeV. So we want to express it in terms of also joule per gram. So let's first look at how many atoms are there in each gram. In each gram, we have 1.00 times 10 to the negative 3 kilogram. But for each gram, because we have 235, that is the atomic number of the atom we're using, so each atom has a mass of 235 mass of proton. So if you plug in the mass of proton, you'll find that each kilogram has 2.55 times 10 to the 21 nucleus. And then we know each nucleus will release 200 MeV energy. So we can again do the unit conversion, 200 MeV of energy times, well, we want to convert this energy to joule, so this is a conversion factor from joule to MeV, and then negative 13. And then we have 2.55 times 10 to the 21 nuclei. Okay. Yeah, so this is 2.55 times 10 to the 21 is the amount of nuclei in each gram. So we already have gram over here. And so this is per gram. So finally, we get this number of 8.2 times 10 to the 10th joule per gram is amount of energy produced by each unit mass. And then part C says, well, okay, let's look at the proton-proton chain that cause the fusion in our sun, and it can be summarized as 6 protons forming 1 nucleus and leaving 26.7 MeV. So we have 6 proton gives us 26.7 MeV. And again, we want to calculate the energy density of this case. So we have 26.7 MeV. And again, we do the unit conversion into joule. And then we divide them by 6 times the mass of proton. So this gives us 4.26 times 10 to the 11 joule per gram. Joule per gram. Okay, so that is for part. Finally, we have part D. I'm going to write it in this corner. So part A, part B, part C and part D. For part D, we are looking at the amount of energy produced by our sun. And so we say that our sun produces energy at a rate of 3.86 times 10 to the 26 watt. And we're assuming that its mass of 1.99 times 10 to the 30 kilogram are all gasoline, which is not true. And then we ask, well, how long would it last if this is actually everything's gasoline? So we found that gasoline produces energy at this rate, at this conversion rate. So 1.99 times 10 to the 30 kilogram times 4.7 times 10 to the 7th jar per gram. Per kilogram. Because here we have per gram, so for per kilogram, we just change 10 to the 4th to become 10 to the 7th. So this is to say the entire sun is able to produce an amount of energy of 9.4 times 10 to the 34 joule. And then at this is the total amount of energy, and then it's producing energy at a rate of 3.86 times 10 to the 26 watt. So if we want to know the total amount of times that it can last, time equals energy over power. So the energy is 9.4 times 10 to the 34 joule. Power is 3.86 times 10 to the 26 watt. If we do this, we will find the total time to be 2.4 times 10 to the 11th second, or 7,600 years. So if our sun were actually made up of gasoline, it will not be able to last very long. But we are glad that our sun is actually dominated by the reaction that is introduced in part C, and we can see this is a much more efficient way of producing energy. We can produce a lot more energy with the same amount of mass.